Calculating standard fundamental constants, like the proton-electron mass ratio, requires exact empirical precision. The official NIST standard places this ratio at 1836.152673. Under the ODTBT geometric framework, the calculated bare mass ratio is 1837.492. That geometric derivation leaves a specific residual error, differing from the NIST value by 0.073%. This paper derives a correction factor to resolve that error. As shown in the abstract, applying this specific term aligns the result to 0.000075% precision. The correction term consists of two components: the fine structure constant, alpha, divided by the integer 10. If the divisor of 10 is a geometric requirement rather than a phenomenological fit, the residual 0.073% error is explained by the symmetry of the basin itself. The paper's entire core thesis is that the integer 10 originates strictly from the topology of an icosahedral zero divergence factor basin. This derivation introduces zero free or tunable parameters. There are no adjustable variables used to align the calculation with the known NIST value. The proof requires the synthesis of three established disciplines: discrete geometry, quantum mechanics, and representation theory. This methodology maps the physical interaction directly onto the symmetry rules of the icosahedral basin. We begin building the geometric stage with a regular icosahedron. We focus on a single vertex and the 5 equilateral triangular faces immediately surrounding it. The spatial boundary of this specific vertex, its Voronoi cell, forms a regular spherical pentagon. To measure the solid angle of this defined space, we apply Euler's polyhedral formula alongside the spherical excess theorem. The calculation reveals that the solid angle of this spherical pentagon is exactly pi/3. Shifting attention to the connecting geometry, exactly 5 full edges intersect directly at this central vertex. By splitting each of those 5 intersecting edges into an incoming and outgoing vector, the space yields exactly 10 distinct directed half-arcs. Therefore, any particle locked within this specific vertex basin is bounded by a pentagon with exactly 10 discrete paths of entry and exit. Now we apply the physics. We place a composite particle, specifically a proton containing 3 internal quarks, into the geometric center of this basin. As the particle occupies this space, its constituent charges accumulate an electromagnetic phase along the pentagonal boundary. This document formalizes the mechanism in equation 6. The phase accumulation is governed by the Aharonov effect, requiring an integration of the vector potential along the geometrical edges. The total scale of this electromagnetic phase coupling is defined by the fine structure constant, alpha. This total coupling force must now interact with the 10 strictly defined geometric paths of the basin, creating a distribution problem. The vertex of an icosahedron is governed by the D5 dihedral group, representing its inherent rotational and reflective symmetries. Applying these D5 symmetry transformations causes the 10 directed half-arcs to map perfectly onto one another. This complete mapping proves that the 10 paths form a single, unbroken mathematical orbit. This geometry triggers a rule from mathematical representation theory known as Schur's lemma. Schur's lemma dictates that any gauge-invariant operator, such as electromagnetic coupling, must assign perfectly equal weight to every element within a single orbit. The total coupling magnitude, alpha, is mathematically forced to decompose perfectly equally across all 10 paths. The alpha/10 fraction is a distribution mandated by the icosahedral symmetry of the vertex. We can now evaluate the physics of specific particles. The proton is a composite hadron containing 3 constituent valence quarks. These 3 quarks act as separate subchannels, triggering the distribution of phase across the 10 edges and applying the alpha/10 damping factor. The electron is an elementary lepton, which is devoid of internal substructure. Operating through a single coherence channel, no phase accumulates over the hadronic edge structure. For the electron, the correction resolves to exactly 0. The mass divergence between a proton and an electron is a structural consequence of how composite and elementary topologies interact with geometric boundaries. Returning to the full formula in the abstract, we insert the derived 1 minus alpha/10 dressing factor. multiplying the bare ratio of 1,837.492 by this geometric dressing factor matches the NIST mass ratio to 0.000075%. This precision was derived through established mathematics without introducing any arbitrary adjustments. The resulting precision suggests that these mass ratios emerge directly from the topological requirements of geometric symmetry.